The formidable sound of 4 Momori power plants reverberated across the vast expanse of the airstrip as the Nakajima Shinzan, Japan's inaugural heavy bomber, commenced its arduous journey along 40,200 feet of reinforced concrete. Possessing an unladen mass of 44,213 pounds, this colossal machine outweighed America's renowned B-17 Flying Fortress by a substantial 8,000 pounds. The skilled test pilot grappled with unresponsive controls as the gargantuan aircraft ultimately ascended into the firmament, achieving a meager climb rate of scarcely 500 feet per minute, which was merely half the ascent capability of its American counterparts. From the observation deck within the hangars below, Chief Engineer Kenichi Matsumura meticulously observed the proceedings through his binoculars, his comprehensive notebook already replete with intricate computations that, in retrospect, should have accurately foretold this precise outcome. In 1939, Japan had strategically acquired the singular Douglas DC-4E prototype for a sum of $275,000. Japanese strategists were profoundly convinced that in this acquisition they had secured the quintessential blueprint for American dominance in aeronautical engineering. Consequently, a painstaking 2-year period of intensive reverse engineering involving the dedicated efforts of hundreds of highly skilled laborers and the application of the finest raw materials available to the Japanese nation, had been invested in constructing their indigenous iteration of what they perceived as American technological superiority. Yet, as the Shinzan gradually vanished into the ethereal morning haze, struggling perceptibly to sustain its precarious altitude, an undeniable and profoundly disheartening realization crystallized. The mere act of replicating American technology often proves insufficient. A deeper, more fundamental comprehension of the underlying design philosophies and strategic rationales that initially guided America's construction choices is absolutely essential. The nascent morning sun painted elongated shadows across the expansive Oda airfield as Kenichi Matsumura meticulously calibrated his stopwatch, poised to observe what the high command of the Imperial Japanese Navy confidently anticipated would represent their definitive countermeasure to the formidable threat of American strategic bombing campaigns. The specific calendar date was April 8, 1941, and the monumental Nakajima G5N Shinzan rested imposingly at the extremity of the runway, resembling a colossal metallic peak. Its quartet of mammary power plants were already undergoing their preparatory warm-up, emitting profound, resonant growls that sent palpable vibrations through the very concrete surface beneath his stance. We invite you to stay with us and watch the conclusion of this compelling narrative. Your support, marked by a like and subscription, would be profoundly appreciated. Please share in the comments where you are viewing from and your thoughts on the subject matter presented in this video. For a period of 18 arduous months, Matsumura had dedicated himself to meticulously supervising the placement of every single rivet and the routing of every electrical wire within this intricate aircraft. He was propelled by a singular consuming obsession that had permeated and driven the entirety of Japan's burgeoning aviation sector ever since the initial strategic planning for Pearl Harbor had commenced. The Americans, it was unequivocally clear, possessed a vital capability that Japan acutely lacked: the capacity to launch devastating strikes against industrial objectives situated an impressive 2,000 miles from their operational bases. The legendary B-17 Flying Fortress, therefore, epitomized a comprehensive array of attributes conspicuously absent from Japan's arsenal: robust and dependable engines, formidable defensive armaments, and, most crucially, the extended operational radius required to project military power deep into adversarial territory. Positioned steadfastly beside the runway, a clipboard firmly gripped in his hand, Matsumura intently observed Major Katsuaki Kira as he methodically executed his comprehensive pre-flight checklist within the confines of the Shinzan's cockpit. The immense bomber extended an impressive 138 feet from its forwardmost point to its rearmost extremity, its lustrous silver aluminum skin shimmering brilliantly under the nascent illumination of the morning. Superficially, on paper, its technical specifications appeared genuinely formidable. An impressive 4,000 kilograms of bomb payload capacity, an extensive operational range of 3,500 miles, and a sophisticated array of defensive armaments strategically positioned to effectively neutralize any encroaching, intercepting enemy fighters. The enthusiastic procurement officials within the Navy had confidently proclaimed it Japan's ultimate war winner, the pivotal aircraft destined to cripple American industrial might. Nevertheless, Matsumura's detailed engineering notebooks presented a decidedly divergent narrative, being replete with intricate calculations that had caused him considerable apprehension for several weeks prior. The reported empty weight stood at a staggering 44,313 pounds. In stark contrast, intelligence reports meticulously gathered from captured B-17G aircraft revealed that American bombers weighed a mere 36,135 pounds when devoid of fuel or weaponry, representing a significant 8,000-pound reduction for the identical mission profile. Such a profound discrepancy fundamentally contravened every established principle of aeronautical design that he had diligently assimilated throughout his distinguished 20-year professional trajectory. The quartet of mammary engines progressively attained their maximum operational power, emitting a sound akin to prolonged rolling thunder. Individually, each of the 4 radial power plants generated a robust 1,270 horsepower, culminating in a combined output of 7,480 horsepower, tasked with elevating a formidable 62,060 pounds at the aircraft's maximum takeoff weight. Matsumura, with ingrained precision, performed the necessary arithmetic instantaneously, yielding a power-to-weight ratio of 120 horsepower per 1,000 pounds. In contrast, the B-17G achieved a superior ratio of 133 horsepower per 1,000 pounds, employing its highly efficient Wright cyclones, which had moreover unequivocally demonstrated their exceptional reliability across hundreds of demanding combat sorties over the European theater. With a decisive action, Major Kira disengaged the aircraft's braking mechanisms, initiating the Shinzan's ponderous takeoff roll. The initial acceleration was noticeably sluggish, gradually building momentum with a deliberate pace that seemed to stretch interminably. The colossal machine traversed 1,000 feet along the runway, then 2,000 feet, and subsequently 3,000 feet. Matsumura's precise stopwatch registered that the bomber had consumed an astonishing 40,200 feet of the concrete surface before its nose wheel finally achieved liftoff. A B-17, under comparable operational parameters, required merely 2,200 feet, less than half the distance, while simultaneously offering a demonstrated 2-fold increase in operational reliability. The Shinzan ascended at what could only be accurately characterized as an exceedingly reluctant and laborious rate, accumulating altitude at a paltry 500 feet per minute. Simultaneously, Major Kira wrestled with flight controls that evinced a responsiveness akin to being immersed in a viscous, heavy oil. Through the powerful magnification of his binoculars, Matsumura could discern the pilot's helmet in perpetual motion, an indication of his continuous, strenuous efforts to counteract the bomber's inherent propensity to wallow aimlessly through the atmospheric currents rather than execute a purposeful, stable flight path. In stark contrast, American B-17s routinely ascended at a brisk 900 feet per minute, their flight crews frequently reporting that the aircraft exhibited an almost eager disposition to attain its designated bombing altitude. As the Shinzan ultimately receded into the morning's diffuse haze, manifestly struggling to sustain its arduous and strained trajectory, Matsumura at last grasped the profound scale and gravity of Japan's fundamental miscalculation. Precisely 2 years prior, in 1939, astute Japanese negotiators had successfully procured the singular Douglas DC-4E prototype for the considerable sum of $275,000, operating under the firm conviction that they had thereby secured the definitive architectural schematic for achieving American dominance in the realm of aviation. This monumental four-engine airliner had initially appeared ideally suited for conversion and adaptation to rigorous military applications, boasting an impressive 138-foot wingspan, robust all-metal construction, a modern tricycle landing gear configuration, and a quartet of potent engines arranged in an identical layout to the formidable B-17. However, the DC-4E had in fact been unequivocally rejected by American Airlines, having been thoroughly assessed and subsequently judged to be excessively complex and prohibitively expensive for viable commercial operations. Both United Airlines, Eastern Airlines, and American Airlines had meticulously scrutinized the prototype and collectively arrived at the conclusion that it was unduly overbuilt, superfluously over-engineered, and intrinsically ill-suited for the demands of profitable air transport service. The very aircraft that Japan had mistakenly believed represented the zenith of American technological prowess was, ironically, nothing less than American industry's most costly and significant commercial setback. Matsumura's dedicated engineering team had undertaken the painstaking task of reverse engineering every individual component of the DC-4E with extraordinary meticulousness and precision, operating under the erroneous assumption that the prevailing American design philosophy prioritized sheer structural robustness over aerodynamic efficiency. Consequently, they had further reinforced structural elements that were already inherently overbuilt, integrated additional defensive positions that merely augmented the aircraft's overall weight without imparting any tangible enhancement in operational capability, and equipped it with engines that, while generating sufficient power, conspicuously lacked the requisite reliability essential for enduring protracted combat engagements. The Momori radial engines, disturbingly, experienced catastrophic failures approximately every 50 flight hours, necessitating comprehensive overhauls that devoured precious, irreplaceable materials and the invaluable expertise of highly skilled labor. In stark contrast, the Wright Cyclones utilized in American service consistently demonstrated the capacity to operate reliably for an impressive 400 hours between major scheduled maintenance interventions. The profound irony of the situation was undeniably devastating. Japan had dedicated 2 exhaustive years and expended millions of yen in a meticulous endeavor to replicate an aircraft that American engineers had already discarded as commercially unfeasible. Yet, In their aspiration for military adaptation, they had inexplicably rendered it even more ponderous and intricate. Every single calculation meticulously recorded in Matsumura's comprehensive notebooks unequivocally corroborated the disheartening revelation from that morning's flight test. The Shinzan, at its very core, harbored a fundamental design flaw, standing as a magnificent testament to precision engineering misapplied to an inherently unsuitable foundation. A cacophony of radio static abruptly erupted from the control tower as Major Kira, with a tone of palpable concern, relayed his current position, barely 20 minutes into the flight. While the crucial service ceiling tests were slated for a later stage, the preliminary indications ominously suggested that the Shinzan would face an arduous struggle to attain an altitude of 24,000 feet under the demanding rigors of combat conditions. In stark contrast, the formidable B-17s routinely navigated the skies at a commanding altitude between 25,000 and 30,000 feet, adroitly leveraging this superior elevation as their primary defensive bulwark against any intercepting fighter aircraft. These American behemoths operated within an atmospheric stratum that Japanese fighters could scarcely hope to reach, effectively transforming the very sky into an impenetrable defensive terrain. As Matsumura retraced his steps toward the engineering hangar, his mind was already relentlessly processing the unsettling implications of the morning's stark failure. Japan, he acutely realized, harbored an urgent and desperate need for strategic bombers. But the strategy of merely replicating American technology had demonstrably proven to be woefully insufficient. The initial acquisition of the DC-4E had been predicated on the erroneous assumption that merely possessing enemy hardware would automatically confer enemy capability. However, true capability, he now understood with painful clarity, did not reside within the sterile confines of blueprints, but rather within the profound industrial philosophy that gave rise to those very blueprints. Stay with us and watch the end of the video. We will be grateful for your like and subscription. What is your opinion on the topic? Where are you from? American aircraft designers, it became evident, did not simply construct flying machines. They meticulously engineered flying machines that possessed the inherent capacity to be manufactured by the thousands, maintained with relative ease by minimally trained mechanics, and operated with unwavering reliability under the brutal conditions of combat by crew members as young as 20 years old. Japanese engineers, conversely, crafted veritable masterpieces that demanded the incessant attention of highly skilled craftsmen, aircraft that, while undeniably sophisticated in their technical execution, were regrettably fragile in their operational reality. The Shinzan, Matsumura knew with a heavy heart, would never progress to full production. Even as Major Kira meticulously completed his test flight and commenced preparations for landing, Matsumura harbored the profound certainty that Japan's initial foray into replicating American strategic bombing capability had faltered even before it had truly begun. Yet, in this moment of profound disappointment, he also recognized a glimmer of hope. Failure, he mused, might impart invaluable lessons that the intoxicating allure of success could never possibly provide. The arrival of spring at Nakajima's Kisumi facility brought with it a renewed sense of pressing urgency, fueled by the unwavering conviction emanating from Imperial Navy headquarters that Japan's strategic bomber program still held the potential to deliver a decisive victory. Despite the Shinzan's profoundly disappointing performance, Admiral Isoroku Yamamoto's esteemed staff had issued a fresh set of directives that verged on the impossible: to develop a formidable heavy bomber capable of reaching the American mainland within a mere 18 months, or else witness Japan's fleeting window of opportunity irrevocably close forever. Kenichi Matsumura found himself relentlessly toiling for 16 hours a day, his engineering team having expanded exponentially to encompass over 200 highly specialized individuals, each meticulously drawn from every major aircraft project across Japan. The Navy's unshakable faith in the Shinzan remained steadfast, a conviction largely based on specifications that appeared impressively robust when meticulously transcribed onto official procurement documents. A substantial 4,000 kilograms of bomb capacity, an extensive 3,500 miles of operational range, and a formidable defensive armament comprising 4 20mm cannons and 12 7mm machine guns. On paper, this aircraft seemed unequivocally capable of inflicting devastating damage upon American industrial targets, spanning from the Aleutian Islands to the sun-drenched coast of California. However, Matsumura's rigorous flight test data painted an entirely different and increasingly troubling picture, one that grew more disquieting with each successive mission. The Shinzan's maximum speed, a mere 261 mph, rendered it acutely vulnerable to any modern fighter aircraft, while its service ceiling of 24,450 feet left it perilously exposed to interceptors that could launch attacks from superior altitudes with absolute impunity. American P-38 Lightnings, according to meticulously analyzed captured intelligence reports, possessed the capability to ascend to a staggering 39,000 feet and achieve speeds in excess of 400 mph during their terrifying diving attacks. KPB. The persistent engine reliability problems proved even more catastrophic than the acknowledged performance shortcomings. The mammary radial engines necessitated complete overhauls every 50 flight hours, a process that ravenously consumed precious aluminum alloy, a resource Japan could scarcely afford to allocate. Each of these intricate engines contained components machined to tolerances so exacting that they demanded the expertise of Japan's most skilled workers, men who were desperately needed for the burgeoning Zero fighter production as the war inexorably expanded across the vast Pacific. Worse still, the mammary power plants generated severe vibrations that not only loosened critical instruments and cracked vital fuel lines, but also fatigued the airframe structures at an alarming and unsustainable rate. In stark contrast, the Wright Cyclones salvaged from captured B-17s exhibited wear patterns entirely consistent with a remarkable 400 hours of operation between major maintenance interventions. American engine design philosophy, it became strikingly clear, placed a paramount emphasis on reliability over sheer peak performance, willingly accepting a slightly reduced power output in exchange for dramatically enhanced operational availability. A typical B-17 squadron could thus maintain combat readiness for months on end, whereas Shinzan bombers, it was painfully evident, would spend considerably more time languishing in maintenance hangars than actively participating in combat missions. Matsumura's dedicated team had initiated detailed examinations of Wright R-1820 engines meticulously removed from B-17s shot down over the Philippines, and the profound differences in manufacturing philosophy were immediately and unequivocally apparent. American cylinders utilized simpler cooling fin designs that were perfectly suited for mass production on automated machinery, while Japanese engines featured intricate cooling patterns that necessitated individual hand finishing by master craftsmen. American connecting rods were robustly forged from standardized steel alloys, whereas Japanese rods employed exotic metals that, while improving performance, invariably created crippling supply chain bottlenecks. The fundamental problem, it was now understood, extended far beyond individual components to encompass the entire industrial approach. American aircraft manufacturers meticulously designed for mass production from the very initial drawing board stage, thereby creating aircraft that could be efficiently assembled by workers with minimal training using standardized tools and procedures. Japanese designers, conversely, optimized for unparalleled performance and exquisite craftsmanship, consequently creating aircraft that demanded skilled artisans at every single stage of production. The inevitable result was bombers that performed magnificently when brand new but degraded rapidly under the unforgiving conditions of combat, requiring constant and specialized attention from specialists who were becoming increasingly difficult to replace. The replacement of such a critical asset proved exceedingly challenging. By the summer of 1941, the ambitious Shinzon program had already absorbed an immense quantity of resources, equivalent to the construction of 300 advanced fighter aircraft, yet it had yielded a mere 6 prototype bombers. The pace of production, which might have appeared satisfactory during the tranquil period of peacetime strategizing, was revealed as catastrophically inadequate once the global conflict escalated, far beyond anyone's initial estimations. In stark contrast, American manufacturing facilities were already churning out B-17 flying fortresses at an impressive rate of 20 aircraft monthly from individual production lines, with plans for numerous additional sites to be activated as military procurement orders continued their upward trajectory. A persistent issue that had plagued the Shinzon since its maiden flight, its excessive weight, only intensified as more and more vital equipment was integrated. The addition of robust armor plating, intended to safeguard critical internal systems, contributed an extra 200 pounds to its mass. Further enhancements to its defensive armament scheme piled on another 800 pounds. Crucially, the incorporation of self-sealing fuel tanks, deemed absolutely essential for any hope of survivability deep within hostile airspace, incrementally boosted the aircraft's empty weight by a substantial 1,500 pounds. Each subsequent modification, though conceived to bolster its combat effectiveness, paradoxically eroded the bomber's already tenuous performance capabilities. This created a relentless, self-defeating cycle where improvements designed to enhance survival ultimately rendered the aircraft too sluggish to evade the very threats it was fortified against. We invite you to stay with us and watch the end of this insightful video. Your support, through a simple like and subscription, would be greatly appreciated. Please also consider leaving a comment below, sharing where you are from and what your thoughts are on the compelling topic discussed in this video. Engineer Matsumura's meticulous calculations starkly illustrated the Shinzon's alarming limitations. A fully laden bomber, carrying its maximum complement of fuel and ordnance, would struggle profoundly to maintain altitude, should even a single engine fail. Its flight characteristics, when operating on twin engines, bordered on perilous, and its single-engine performance rendered any prospect of a successful emergency landing highly dubious, at best. In stark contrast, intelligence reports indicated that American B-17 crews routinely managed to guide their battle-damaged bombers safely back to base on just 2 engines, and there were even documented instances of aircraft returning after having lost half of their power plants to fierce enemy engagements. The pervasive aluminum shortage, which began to exert its detrimental influence across all facets of Japanese aircraft production in late 1941, impacted the Shinzan program with particular severity. Each of these heavy bombers demanded an extraordinary 8 tons of aluminum alloy for its construction, a significant increase compared to the 5 tons required for a nimble Zero fighter or the 3 tons typically needed for a standard Army bomber. Theoretically, Japan's entire national aluminum production capacity could sustain the manufacture of 12 Shinzan bombers per month. However, this output was only achievable under the impossible condition that no other aircraft whatsoever were produced simultaneously. The harsh realities of wartime priorities dictated that the production of heavy bombers like the Shinzan found itself in direct competition with urgent fighter programs, which were desperately needed for the defense of the home islands. According to intelligence assessments, American aluminum production surged past 900,000 tons annually by 1943. In contrast, Japanese production reached its zenith at a mere 142,000 tons in 1944, a colossal resource disparity that rendered any large-scale bomber production impossible, irrespective of how efficient or groundbreaking a design might be. Even if Matsumura's dedicated team had somehow engineered an absolutely flawless aircraft, Japan simply lacked the fundamental industrial capacity to construct it in strategically meaningful quantities. The escalating psychological toll on his engineering team became increasingly palpable as persistent test flights relentlessly exposed fundamental design flaws. Dedicated workers who had invested countless months meticulously perfecting individual components were forced to observe helplessly as their painstaking craftsmanship was effectively nullified by systemic design deficiencies that defied correction through mere incremental adjustments. The Shinzan, in essence, demanded a complete overhaul, a radical redesign from its foundational principles. Yet the unyielding Navy procurement schedules afforded absolutely no allowance for such a drastic restart. By the autumn, Matsumura had arrived at a profound, albeit unspoken, conclusion that he dared not articulate in formal official meetings. Japan was fundamentally constructing the incorrect aircraft, employing inappropriate methodologies for a strategic situation that was entirely ill-suited to its capabilities. The Shinzan, in a cruel twist of fate, embodied everything that Japanese engineering typically excelled at: meticulous precision manufacturing, an unwavering attention to minute detail, and the exquisite optimization of individual components. But it applied these strengths to a mission that necessitated precisely what Japanese industry struggled with: large-scale mass production, simplified maintenance protocols, and a design philosophy prioritizing rugged reliability over absolute perfection. The captured B-17s, now resting within Japanese hangars, served as potent daily reminders of a fundamentally different approach to aviation engineering. However, merely comprehending the intricate American design philosophy and effectively implementing it within the existing Japanese industrial framework presented entirely distinct and formidable challenges. Japan undoubtedly possessed the technical acumen and knowledge required to construct superior bombers, but it critically lacked the expansive industrial infrastructure necessary to build them in numbers significant enough to influence the strategic trajectory of the war. The eagerly anticipated captured B-17E arrived at Nakajima's sprawling facility via a flatbed truck convoy in March of 1942. Its aluminum skin bore the unmistakable scorch marks from the fierce fighter attack that had ultimately forced its descent in the Philippines. Kenichi Matsumura himself stood stoically beside the cavernous hangar doors as skilled workers meticulously maneuvered the remarkably intact bomber inside, a complex cocktail of anticipation and professional dread churning within him. For the preceding 18 months, his dedicated team had been painstakingly reverse engineering a DC-4E prototype, operating under the assumption that they had grasped the essence of American design philosophy. Now, at long last, they would have the unprecedented opportunity to examine the authentic article, the genuine, real thing. Initially, the imposing flying fortress appeared somewhat smaller than anticipated, its wingspan of 103 feet seeming almost elegantly delicate when juxtaposed against the Shinzan's own colossal 138-foot spread. However, as Matsumura's specialized inspection team commenced their systematic and rigorous examination, the profound underlying differences began to emerge with a clarity that fundamentally challenged every single assumption they had held regarding American engineering prowess. The B-17's empty weight, recorded at 36,135 pounds, was an astonishing 8,000 pounds lighter than that of the Shinzan, despite both aircraft carrying a comparable array of defensive armament and possessing similar fuel capacities. Matsumura personally oversaw the intricate engine removal process, intently observing as expert technicians meticulously extracted the powerful Wright R-1820 Cyclone radials, the very engines that had propelled this particular fortress across thousands of unforgiving miles of the vast Pacific Ocean. Each of these robust engines weighed 1,850 pounds and was capable of generating a potent 1,200 horsepower at takeoff settings. In contrast, the Shinzan's Memori engines, while individually heavier at 2,100 pounds each, produced a higher output of 1,070 horsepower. This initially seemed to create a more impressive power-to-weight ratio for the Japanese bomber. But this perception quickly dissolved when compared against the superior American efficiency standards. The Wright Cyclones exhibited wear patterns that eloquently recounted a remarkable narrative of unwavering operational reliability. Their cylinder walls displayed an even scoring, perfectly consistent, with hundreds of sustained flight hours, while the connecting rod bearings showed only minimal degradation, astonishingly, despite clear evidence of combat stress. Perhaps the most startling revelation was the sheer simplicity of the cooling system design. Straightforward, unadorned fins, precisely machined with automated equipment, a stark departure from the complex, intricately curved patterns that Japanese engineers had long presumed were absolutely indispensable for achieving adequate heat dissipation. Equate heat dissipation. Upon dismantling the American engines, a distinct manufacturing ethos became apparent, one that profoundly contradicted every principle of meticulous engineering Matsumura had internalized throughout his career. While their tolerances were notably more permissive than the stringent Japanese benchmarks would permit, these power plants consistently demonstrated superior operational dependability compared to the Mamori radial engines, despite the latter's construction to far more exacting specifications. Evidently, American engineers had prioritized sustained operational integrity over maximal output, willingly trading a marginal decrease in efficiency for a substantial enhancement in ease of maintenance and overall reliability. The disparities observed in the airframe's structural composition offered even deeper insights. The wing spars of the B-17, for instance, were crafted from aluminum extrusions, a material readily amenable to large-scale production via rolling mills. Their design strategically focused reinforcement at critical stress points, rather than disseminating it uniformly across the entire framework. Conversely, Japanese engineers had constructed the wings of the Shinzan using intricate forgings, each demanding individual precision machining. While these components might have possessed theoretical advantages in terms of inherent strength or aerodynamic purity, their production methodology rendered them virtually unfeasible for mass manufacturing, creating a significant bottleneck in output. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Matsumura dedicated considerable time to scrutinizing the B-17's electrical architectures, marveling at the pervasive standardization, a design philosophy that ensured any single electrical component could be swapped out with minimal specialized instruction. The wiring harnesses exemplified this, featuring clearly defined color-coded insulation and universally compatible connectors, thereby eradicating ambiguity during essential field maintenance operations. Furthermore, control cables were intelligently channeled through easily accessible conduits, punctuated by inspection plates at regular intervals, empowering ground crews to swiftly pinpoint and rectify any issues. In stark contrast, the Shinzan's electrical frameworks necessitated a deep, specialized understanding for servicing, burdened by bespoke connectors and concealed routing, which inevitably transformed troubleshooting into an arduous and protracted endeavor. The methodology for integrating defensive armament unveiled yet another foundational divergence in design philosophies. B-17 gun emplacements were conceived for expeditious fitting and detachment, featuring standardized mounting brackets capable of housing various weapon configurations in response to evolving mission dictates. Their ammunition supply mechanisms relied on straightforward mechanical designs, exhibiting remarkable resilience against jamming, even amidst the rigors of aggressive aerial maneuvers. Japanese defensive systems, conversely, prioritized pinpoint accuracy and sheer offensive capability, employing sophisticated hydraulic apparatuses that, while offering enhanced precision, demanded continuous fine-tuning by highly proficient armorers. Even the flight control systems within the captured flying fortress, functioning through an array of cables and pulleys, appeared almost rudimentary when juxtaposed with the advanced hydraulic boost systems prevalent in Japanese aircraft. Nevertheless, American aviators consistently lauded its exceptional handling attributes across the full spectrum of operational scenarios. These mechanical controls offered immediate, tactile feedback, enabling pilots to acutely perceive the onset of stall conditions, whereas hydraulic boost systems could dangerously obscure critical flight attitudes until a point of no return was reached. Matsumura's profound insight crystallized. Simplicity, far from denoting engineering inferiority, served as compelling proof of a more refined and effective design philosophy. The architecture of the fuel system unequivocally underscored American design priorities with stark transparency. The fuel tanks of the B-17 were fabricated from uncomplicated aluminum sheeting, incorporating resilient rubber bladders that were readily interchangeable in field environments, using only fundamental tools. Their inherent self-sealing prowess stemmed from specialized rubber compounds designed to automatically seal minor perforations, thereby offering vital protection without recourse to intricate mechanical components prone to failure amidst the pressures of combat. In contrast, Japanese fuel systems incorporated complex pumps and valves, engineered for meticulous fuel regulation, yet inadvertently introducing numerous potential points of failure, a critical vulnerability that could leave aircraft stranded far from their operational bases. As the summer of 1942 progressed, and Matsumura's team meticulously assembled their comprehensive analysis, a profound realization dawned upon him regarding the immense scale of Japan's strategic miscalculation. It became strikingly evident that American engineers were not merely constructing individual aerial vehicles. Rather, their ingenuity was directed towards conceiving entire production ecosystems capable of churning out thousands of aircraft, utilizing a workforce requiring only rudimentary training. Consequently, every single component was meticulously optimized for ease of mass production, simplified field maintenance, and unwavering operational dependability, rather than being singularly focused on achieving maximal performance metrics or exhibiting sheer engineering sophistication. The quantifiable data presented a stark and devastatingly clear narrative. Production figures for the B-17 had already escalated to an impressive 48 aircraft, monthly solely from Boeing's Seattle plant, with further manufacturing lines slated for activation as military procurement contracts expanded. Each flying fortress necessitated approximately 15,000 man-hours for its full completion, a stark contrast to the 32,000 man-hours required for just one Shinzan prototype. This disparity meant that American laborers possessed the capacity to construct 3 of these formidable heavy bombers in the same time frame. It took skilled Japanese artisans to finalize a single equivalent aircraft. Comparisons in material consumption provided an equally sobering perspective. A B-17 utilized 2 tons of aluminum alloy, whereas the Shinzan demanded a substantially greater 1 tons to achieve a comparable operational capacity. American designers had judiciously eradicated superfluous material through a rigorous, systematic analysis of stress distribution, thereby fashioning airframes that possessed precisely the requisite strength to fulfill operational demands, devoid of any unnecessary weight that would compromise performance. Japanese engineers, conversely, had constructed airframes exhibiting strength beyond necessity, operating under the presumption that superfluous robustness was inherently superior to a meticulously optimized design. The contrasting maintenance philosophies became strikingly evident upon careful scrutiny of the captured bombers' operational logbooks, which had been retrieved undamaged from the wreckage. B-17 squadrons executed routine scheduled maintenance following standardized protocols, tasks readily accomplished by any competent mechanic in a field setting. For instance, an engine replacement could be completed within 6 hours, utilizing standard tools, and repairs to the hydraulic system merely called for fundamental mechanical aptitude. Shinzan upkeep, however, necessitated the expertise of specialized technicians intimately familiar with the idiosyncratic traits of each individual aircraft. rendering squadron-level repairs utterly impractical amidst the exigencies of combat. Perhaps the most telling revelation emerged from the American methodology concerning battle damage rectification. B-17 airframes were engineered for graceful failure, meaning damage tended to localize at particular points, allowing for expedient field patching. Aluminum skin panels, for example, could be substituted with sections salvaged from other damaged aircraft, while structural reinforcements typically employed standard aluminum angle stock, readily procurable from any industrial vendor. Conversely, Japanese aircraft mandated bespoke components, manufactured to exacting specifications, thereby precluding field repairs and consigning compromised aircraft to lengthy periods out of commission. By October of 1942, Kenichi Matsumura had arrived at a profound realization, a conclusion poised to fundamentally reorient Japan's entire strategic approach to the development of heavy bombers. His extensive analysis revealed that the formidable B-17 Flying Fortress did not owe its preeminence to some exotic, cutting-edge technology or the deployment of rare, advanced materials. Instead, its true superiority stemmed from American engineers' astute decision to tackle the most pertinent challenge. Rather than striving for an aircraft of theoretical perfection, they had meticulously crafted a bomber robust enough to be readily manufactured, easily maintained, and reliably operated by average personnel, even when confronted with the most extraordinary and demanding combat scenarios imaginable. This pragmatic philosophy, focused on widespread utility and resilience, was the true bedrock of its success. The path forward, illuminated by this critical insight, was undeniably clear, yet presented a formidable challenge. Japan faced the urgent necessity of completely abandoning the Shinzan program, a project already well underway, and embarking anew with the American design philosophy as its foundational principle. However, with 18 months having already elapsed since the Pacific War's commencement, the precious commodity of time was rapidly diminishing for such a radical and fundamental shift in strategic orientation and developmental methodology. The urgency of the situation underscored the immense pressure on Matsumura and his team to enact sweeping changes with unprecedented speed. The pivotal telegram from Imperial Navy headquarters reached the Nakajima's Koizumi facility on September 14, 1943. Its contents unveiled a set of specifications that, in their sheer ambition, appeared crafted more to ignite fervent aspiration than to provide tangible, practical guidance for engineers. We sincerely hope you are finding this narrative insightful and engaging. Please stay with us and watch the end of the video to grasp the full scope of this historical endeavor. We would be incredibly grateful for your like and subscription, which helps us continue bringing these stories to life. Additionally, we invite you to share in the comments where you are from and what your thoughts are on this fascinating topic of wartime engineering philosophy. Kenichi Matsumura meticulously reviewed the demanding requirements twice over before carefully placing the document upon his drafting table. He grasped with absolute clarity that Admiral Yamamoto's staff had, in essence, issued an imperative for his team to defy the very laws of physics, all while adhering to an incredibly restrictive 18-month deadline. The task before them was monumental, bordering on the miraculous. The enumerated specifications detailed an aircraft of almost mythical capability, a maximum speed of 370 mph, a velocity surpassing that of any extant heavy bomber anywhere in the world. Its service ceiling was stipulated at an astonishing 33,000 feet, an altitude sufficient to allow operations well above the engagement envelopes of most contemporary intercepting fighters. A remarkable range of 4,600 miles was required with a reduced bomb load, making it capable of reaching the American West Coast and subsequently returning to base. Furthermore, a maximum bomb capacity of 8,800 pounds was mandated, an explosive payload deemed ample to utterly devastate significant industrial targets. These requirements, in their collective scope, read less like a sober technical brief and more like an idealized wish list, seemingly penned by individuals who had little to no practical experience in calculating critical power-to-weight ratios or navigating the complex realities of aluminum allocation requirements during wartime. Yet Matsumura, having dedicated a painstaking 18 months to dissecting and studying captured B-17s, possessed a crucial advantage. The profound lessons gleaned from this intensive examination of American engineering philosophy had coalesced into a truly revolutionary insight. He recognized that Japan's fundamental error had been the superficial replication of American hardware, while critically overlooking and failing to adopt the underlying American methodology. The forthcoming bomber, officially designated the G-8N Renzan, or Mountain Range, would thus make a decisive break from the DC-4E template that had previously influenced Japanese designs, instead fully embracing the core design principles that demonstrably underpinned the success of American aircraft. Working sessions throughout that autumn frequently extended far beyond midnight, as Matsumura's dedicated team systematically dismantled and discarded every single assumption that had historically guided Japanese aircraft development since the 1930s. Traditional Japanese engineering, with its profound emphasis on individual craftsmanship and the meticulous optimization of isolated components, had consistently produced aircraft that were undeniably technological marvels, yet simultaneously proved to be manufacturing nightmares. In stark contrast, American engineering championed systematic integration and an unwavering focus on production efficiency, a philosophy that yielded aircraft good enough in design, but crucially capable of being constructed by the thousands, thereby transforming the scale of aerial warfare. The G-8N design that ultimately materialized from these extraordinarily intensive sessions bore absolutely no resemblance to any previous Japanese bomber. Elegant, clean lines superseded the complex, ornate curves that had characterized earlier models. A singular vertical stabilizer was adopted, effectively eliminating the cumbersome twin-tail configuration that had persistently plagued the Shinzon's directional stability. Mid-mounted wings were incorporated, offering enhanced structural efficiency, while simultaneously improving crucial access for ground maintenance crews. Every single component was conceived with a clear hierarchy of priorities: reliability first, followed by performance second, and finally, manufacturing ease third, a radical reordering of priorities that directly reversed the entrenched philosophy of traditional Japanese aircraft development. The selection of the power plant emerged as an absolutely critical determinant for the entire program's ultimate success. Rather than the conventional approach of adapting existing, perhaps suboptimal engines, Matsumura successfully persuaded Navy procurement officials to allocate funding for the dedicated development of the Nakajima NK9KL Homar radial engine, specifically tailored for the demanding G-8N mission. Each individual engine was designed to generate a robust 2,000 horsepower at military power settings, collectively providing an impressive 8,000 total horsepower to propel an aircraft projected to weigh 38,360 pounds empty. This formidable power-to-weight ratio was finally poised to match American standards, while simultaneously aspiring to exceed American performance benchmarks. The Homar engines thoughtfully incorporated invaluable lessons gleaned from the meticulous teardowns of captured Wright Cyclone engines, placing a paramount emphasis on operational reliability over the pursuit of mere peak performance figures. The cylinder cooling fins featured simplified designs, specifically chosen for their amenability to mass production techniques, while internal components were meticulously manufactured to tolerances that expertly balanced the need for precision with the imperative of production speed. Furthermore, the supercharging systems were specifically optimized for high-altitude operation, ensuring the delivery of full power output at altitudes where enemy intercepting fighters would inherently struggle to maintain their formation and operational effectiveness. Airframe construction represented another significant departure, abandoning the intricate forgings and custom machining processes that had rendered the Shinzan prohibitively expensive and time-consuming to manufacture. The G8N wing spars ingeniously utilized aluminum extrusions, components that could be efficiently produced on standard rolling mills. Reinforcement was strategically concentrated at points of high stress, rather than being distributed uniformly throughout the entire structure, optimizing both strength and weight. Moreover, skin panels were deliberately designed for easy replacement using common shop tools, a critical feature allowing for rapid battle damage repair even under challenging field conditions, thus enhancing the aircraft's operational availability. The electrical system design profoundly reflected a hard-won, pragmatic understanding of the demanding requirements for combat maintenance. Standardized connectors and a logical color-coded wiring scheme were meticulously implemented to eliminate guesswork during repairs, significantly reducing the time mechanics spent troubleshooting. Simultaneously, accessible routing for all wiring allowed ground crews to quickly trace and diagnose problems. Power distribution ingeniously employed proven American-style bus systems, a marked improvement over the complex switching networks that had previously rendered Shinzan electrical repairs a highly specialized task, often requiring days of painstaking troubleshooting by expert technicians. The fuel system's design prioritized survivability without compromising maintainability, a delicate but crucial balance. Self-sealing tanks were incorporated, utilizing robust rubber bladders that could be readily replaced by squadron-level mechanics, ensuring quick turnaround times. Fuel pumps and valves were strategically positioned for effortless access during scheduled maintenance procedures, simplifying routine checks and repairs. The entire system was engineered to provide precise fuel management, essential for executing extended long-range missions, while deliberately eliminating the complex automation that had previously introduced multiple potential failure points in earlier Japanese designs, thereby enhancing overall reliability. The strategic placement of defensive armament meticulously balanced formidable firepower with critical structural integrity, thereby skillfully circumventing the weight penalties that had consistently plagued previous Japanese bomber designs. Gun positions were engineered with standardized mounts, offering the crucial flexibility to accommodate various weapon types as operational needs evolved. Ammunition feeds relied on robust mechanical systems ensuring reliable functionality even under the violent maneuvering inherent in aerial combat. This comprehensive installation provided extensive defensive coverage across the aircraft's vulnerable zones, all without introducing detrimental drag or excessive weight that would otherwise compromise the bomber's vital flight performance. The first G-8N prototype majestically rolled out of Nakajima's final assembly hangar on August 23, 1944. Its gleaming silver aluminum skin shimmered brilliantly under the intense work lights, which had burned continuously for an arduous 3 months, illuminating the tireless efforts of its creators. Kenichi Matsumura himself personally oversaw the meticulous pre-flight inspection, carefully scrutinizing every system and component, a culmination of 4 years of painstakingly accumulated knowledge regarding the essential factors that truly made an aircraft successful and resilient under the unforgiving crucible of combat conditions. Test pilot Captain Teiichi Shirani embarked upon the inaugural flight of the G-8N on October 23, 1944, subsequently delivering a report that lauded its handling characteristics as far exceeding all prior expectations. The aircraft's impressive maximum speed of 368 mph, achieved at an altitude of 245 feet, convincingly validated the sophisticated design calculations that had optimistically predicted performance levels comparable to American standards from Japanese manufacturing. Further rigorous service ceiling tests confirmed that this formidable aircraft could operate effectively at 33,465 feet, an altitude significantly above the typical operational band, where most intercepting fighters could maintain their combat effectiveness. Range testing proved equally remarkable, with a maximum distance of 4,639 miles, meticulously demonstrated during carefully monitored fuel consumption flights. This extraordinary reach meant the G-8N possessed the capability to strike targets on the American West Coast and subsequently return to bases located in the Mariana Islands, thereby finally bestowing upon Japan the strategic bombing capability that had been a core promise since the nascent stages of Pearl Harbor planning. However, even as the third prototype was undergoing its final acceptance trials at Koizumi Airfield in early 1945, the broader strategic landscape that had initially justified the G-8N program was rapidly deteriorating, collapsing beyond any hope of recovery. Relentless American B-29 superfortresses were systematically dismantling Japan's industrial capacity, while carrier-based aircraft roamed with impunity across the Japanese home islands. Consequently, the crucial aluminum necessary for G-8N production was being urgently diverted to defensive fighter programs, which offered a more immediate, albeit desperate, form of protection against the devastating bombing campaign that was reducing Japan's once thriving cities to mere ash and rubble. The harsh realities of the war effort dictated a shift from ambitious offensive capabilities to a desperate struggle for homeland defense, leaving the promising G-8N in an increasingly precarious position. Ultimately, a mere 4 G-8N prototypes would be completed before Japan's unconditional surrender brought a permanent cessation to the program. The aircraft that had finally offered a viable solution to Japan's long-standing strategic bomber deficiency had arrived tragically late to exert any meaningful influence on the war's predetermined outcome. It stood as an undeniable masterpiece of engineering, yet it was ultimately rendered irrelevant by the unyielding calculus of industrial output, a numerical disparity that no amount of technical brilliance or design ingenuity could possibly overcome. The sheer scale of wartime production dictated victory, a metric where Japan simply could not compete. As we continue to delve into the fascinating, albeit tragic, narrative of the G8N, we invite you to stay with us and watch the conclusion of this insightful video. Your engagement truly supports our efforts, and we would be immensely grateful for your like and subscription. Please also share your thoughts in the comments below, letting us know where you are watching from and what your perspective is on the profound implications of this particular historical topic. Kenichi Matsumura, a pivotal figure in the G8N's development, observed the fourth prototype as it taxied to its designated parking position on August 10, 1945. A profound realization settled upon him. American technical teams would soon arrive to meticulously examine what Japanese engineering could truly accomplish when liberated from the historical constraints of merely replicating foreign designs. The G8N, in his eyes, epitomized the culmination of everything Japan had painstakingly learned about constructing aircraft the correct way, representing a significant leap in indigenous design. Yet, the arduous journey of learning the right way had consumed far too much time, rendering its strategic impact negligible in the grand scheme of the conflict. The somber announcement of Japan's surrender reached Nakajima's Koizumi facility precisely at noon on August 15, 1945. It was transmitted through radio speakers that crackled with static, carrying the Emperor Hirohito's solemn voice as he conveyed to the Japanese populace that the devastating war had finally concluded. Kenichi Matsumura stood motionless within the engineering hangar, positioned directly beside the majestic fourth G8N prototype, watching his dedicated team of 200 specialists slowly absorb the crushing reality that 4 years of intensive, unremitting development had culminated not in triumph, but in Japan's unconditional defeat. Outside the hangar, a stark and poignant contrast unfolded. American B-29 superfortresses relentlessly continued their systematic campaign of destruction against Japanese industrial capacity. Their telltale contrails remained visible at altitudes that the G8N could theoretically reach, yet would never operationally challenge or contest. The irony was absolute and profoundly bitter. Japan had, at long last, succeeded in creating a strategic bomber capable of matching or even exceeding American performance, precisely at the moment when American strategic bombers had completed their mission of eliminating Japan's fundamental ability to manufacture aircraft in any meaningful quantities. The window of opportunity had closed irrevocably. The devastating numbers that unequivocally defined the program's ultimate failure were etched into Matsumura's memory with an almost mathematical precision, a constant reminder of the insurmountable odds. He reflected on the mere 4 G8N prototypes that had been completed, a stark contrast to the colossal 12,731 B-17 flying fortresses churned out by American factories. These 4 aircraft, representing the zenith of Japanese engineering achievement, stood against an American production line that in a single month delivered more bombers than Japan had managed to construct during 4 years of concentrated, exhaustive effort. The quantitative chasm was simply too vast. American technical intelligence teams made their arrival at Koizumi on September 3, 1945. Led by Colonel Harold Watson, a distinguished figure from the Army Air Force's Technical Intelligence Unit, Matsumura personally guided the examination of the G8N prototypes. He meticulously elucidated the intricate design decisions and the impressive performance characteristics to the American engineers, who approached the advanced aircraft with a discernible professional curiosity, rather than any overt, triumphant satisfaction. Their interest was rooted in objective assessment, not in celebrating victory. The array of captured German and Japanese aircraft they were documenting, including the G-8N, collectively represented remarkable technological achievements that had, regrettably, arrived too late to significantly alter the trajectory of the war's outcome. Colonel Watson's subsequent assessment, meticulously recorded in technical reports that would remain classified for many decades, acknowledged the G-8N's truly impressive capabilities. However, his analysis simultaneously highlighted the profound industrial limitations that had inevitably doomed the program, underscoring the critical distinction between individual technical prowess and the capacity for mass production. The G-8N's maximum speed of 368 mph actually surpassed early B-29 performance figures, while its service ceiling of 33,465 feet admirably matched the robust standards of American heavy bombers. Furthermore, its impressive range capability of 4,600 miles would have theoretically enabled devastating strikes against the continental United States from bases established in the Marshall Islands. Yet, these performance specifications, while compelling, revealed only a partial truth. Watson's expert team calculated that manufacturing a single G-8N required approximately 42,000 man-hours of highly skilled labor, an astonishing figure when compared to the 18,000 man-hours needed for a B-29 Superfortress constructed on Boeing's highly automated production lines. While Japanese craftsmanship undoubtedly produced aircraft that were technically superior in their individual components, American mass production created aircraft that were strategically decisive through their sheer, overwhelming, numerical superiority. The material consumption analysis unveiled even starker and more revealing contrasts. Each G-8N prototype consumed a substantial 7 tons of aluminum alloy, whereas American heavy bombers, through systematic optimization of their structural design, averaged a more efficient 2 tons. Japan's total aluminum production in 1944 reached its peak at 142,000 tons, a quantity theoretically sufficient to construct 16,000 G-8N bombers, assuming no other aircraft were manufactured concurrently. In sharp contrast, American aluminum production in 1943 alone exceeded a staggering 920,000 tons, providing ample resources to support the simultaneous production of fighters, bombers, transport aircraft, and even civilian goods, without encountering debilitating resource allocation conflicts. Matsumura, in his interactions with American interrogators, found himself compelled to elaborate on the fundamental philosophical differences that had profoundly shaped Japanese aircraft development throughout the entire war. Traditional Japanese engineering, he explained, placed an overriding emphasis on the meticulous perfection of individual components. This approach, while resulting in aircraft that were veritable marvels of precision manufacturing, simultaneously created nightmares of production complexity. Conversely, American engineering prioritized the seamless integration of adequate components into highly effective systems, thereby creating aircraft that could be efficiently manufactured by workers with minimal specialized training, following standardized and streamlined procedures. The meticulous establishment of standardized procedures proved to be a critical differentiator. The comparative analysis of engine development, in particular, offered profoundly insightful lessons for American technical teams engaged in scrutinizing the outcomes of the Pacific War. The Nakajima NK9KL Homar radial engines powering the G-8N each capable of generating 2,000 horsepower through supercharging systems that represented the pinnacle of Japanese technological advancement, nonetheless demanded complete overhauls every 120 flight hours. This frequent maintenance was necessitated by inherent deficiencies in the material composition of high-stress components. In stark contrast, the Wright R-3350 Cyclone engines integrated into the B-29 Superfortress produced a robust 2,200 horsepower and could operate for an impressive 400 hours between major maintenance cycles. This superior endurance was the direct result of systematic reliability engineering, a design philosophy that placed a premium on sustained operational readiness rather than merely achieving theoretical maximum power output. Discrepancies in manufacturing philosophy pervaded every facet of aircraft production. For instance, the G-8N's wing spars were meticulously machined from solid aluminum billets, a process that utilized precision tooling and required hours of intricate setup time for each individual component. Conversely, the B-29's wing spars were ingeniously assembled from aluminum extrusions and sheet metal stampings. These elements could be churned out on an industrial scale using automated machinery often operated by semi-skilled workers, while Japanese methodologies undeniably yielded components that were inherently more robust and structurally superior. American approaches delivered entirely adequate components in such prodigious quantities that they utterly overshadowed any marginal gains in individual component quality or performance. The comprehensive analysis of maintenance requirements uncovered stark operational truths that had remained entirely obscured during the tranquility of pre-war design phases. The G-8N's intricate systems demanded specialized tools and highly trained mechanics for even routine servicing, rendering on-site, frontline servicing an insurmountable challenge under the intense pressures of combat conditions. Conversely, the B-29 systems were deliberately engineered for ease of maintenance, allowing mechanics with basic training to perform repairs using common tools readily available at any forward airfield. Consequently, a damaged Superfortress could be swiftly restored to a battle-ready state within mere hours, whereas a similarly compromised G-8N would face an arduous process demanding weeks of intensive, specialized attention at major maintenance facilities. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. By October of 1945, American technical teams had finalized their comprehensive assessments of Japanese aircraft development programs, formulating pivotal insights destined to shape subsequent military acquisition strategies for numerous decades. Their overarching conclusion was unequivocal: technical excellence, when unaccompanied by robust industrial capacity, was ultimately devoid of any genuine strategic value. The most exquisitely sophisticated aircraft in the world, they determined, proved utterly incapable of offsetting fundamental limitations in manufacturing capability and the efficient allocation of vital resources. Matsumura's final interview with Colonel Watson unfolded alongside the fourth G-8N prototype on November 8, 1945, as American transport crews made ready to transport the aircraft to Wright Field for exhaustive, detailed analysis. The ensuing conversation delved beyond mere technical minutiae to address the overarching systemic elements that ultimately dictated the war's outcome, notwithstanding Japan's notable achievements in individual aircraft performance. The unsparing calculus of industrial warfare, they both acknowledged, had effectively nullified the impact of even the most sophisticated engineering prowess. A staggering 4,750 B-17 flying fortresses were lost in the skies above Germany, a figure that eclipsed the total output of all heavy bomber variants manufactured by Japan across the entire duration of the conflict. American factories, with their immense productivity, replenished their operational inventory at a pace far exceeding that at which Japanese factories could produce new aircraft. This established an insurmountable numerical disparity, which no degree of advanced technical ingenuity could ever surmount. Watson's definitive evaluation, meticulously documented within confidential reports destined to profoundly influence American understanding of industrial warfare for the burgeoning Cold War era, underscored broader principles that transcended the confines of mere aircraft development. Triumph, he asserted, was not the prerogative of states crafting the most exquisitely designed armaments, but rather of those capable of producing serviceable weaponry in prodigious volumes. The G-8N Renzan, in its magnificent design, stood as a testament to the zenith of Japanese engineering capability, when unburdened by material limitations. However, the inescapable truth of contemporary armed conflict lay in the omnipresent and unyielding grip of resource scarcity. Matsumura watched, his gaze fixed as the fourth prototype vanished into the cavernous interior of an American transport vessel's cargo bay, with the profound and poignant realization that his team's crowning engineering accomplishment was destined to become a static museum artifact, rather than a formidable instrument of war. A rigorous 4-year period of dedicated development had culminated in the creation of an aircraft, possessing the inherent capacity to alter the very course of the conflict, had it been possible to produce it in the vast quantities that Japan, regrettably, could never hope to attain. The fundamental insight, grasped with tragic belatedness, was undeniably straightforward.